this is Miss Hickman, and today we're going to be introducing definite integrals. Okay, so in the last section we talked about Riemann sums, which were named after George Friedrich Bernhard Riemann, and he proved the existence of definite integrals. So in this section we're going to be looking at what an integral is, and we're going to see the more familiar look of it. But first, like limits and derivative, you got to see where they come from. So sigma notation. So the Greek letter sigma stands for sum. The index k tells us where to begin. So you see k equals 1. So that's the function you start with. So a of 1 plus a of 2 plus a of 3. And then this up here tells you where to stop. As you can see, you stopped at n. The symbol infinity, if the symbol infinity appears above the sigma, it indicates that the terms go on indefinitely. So LRAM, MRAM, and RRAM are all called Riemann sums because they are constructed in a particular way. So if you look at this, on each subinterval, we form the product f of c to k, so it's some y value, which is going to be the height, times a change in the width of a rectangle. Okay, so if you look here, let's look at this one because I see a C to K right there. So remember, if you remember from the last section, everything was a sum. Well, here's one thing you're looking at. So the height, C of K, times the change in x from x2 to this one. That's what we're looking at. And the K just means the kth rectangle you're looking at. Okay? Which gives us our height times width, which is the area of each rectangle. We then take the sum of these products. So we're going to have sigma notation where k is equal to 1 and goes to n of that. This is a Riemann sum for f on the interval a to b. Okay, so a is right here, b is right there. Okay? All Riemann sums for a given interval in a to b converge to a common value, as long as the lengths of the subintervals all tend to 0. Rectangulars get smaller and smaller. Okay? So the definite integral as a limit of Riemann sums. There's that word again, limits. So let f be a function defined on a closed interval a to b. Okay, great. So it starts at one point and goes to the other point. Okay, great. For any partition P of a to b, let the numbers c sub k be chosen arbitrarily in the subintervals. Yeah, you just pretend that's like x2, x1. If there exists a number I, such that the limit, as the rectangulars are getting smaller, that's what a partition is. The rectangulars are getting closer to 0. So you have this rectangle up here, the rectangles start getting smaller. Okay? They're supposed to be getting smaller. Okay? Each time you converge, they get smaller. So if this was our closed interval from here to here, or we'll go over here, or right here. So let's call this a to b right here. Okay? So you got a rectangle like this. Okay? Great. All right? Now, but it says the limit as a partition is approaching 0. So the width in between them gets smaller. So you're just going to add more rectangles. And then you're going to get smaller until it's pretty much closer enough to 0. Okay? So the limit as the partitions approach 0 of k equal to 1 of n will give you, there's the area, height times width equals some number I. No matter how p and the c sub k's are chosen, the f is integrable on a to b, and I is a definite integral of f over a to b. I'm guessing that's a typo there. Bye. Alrighty? So a partition determines the number of closed subintervals. Change in x is going to be b minus a over n. So as p gets smaller, a definite integral forms. Okay, so this is what a partition is. Your change in x is getting smaller and smaller, just like we started here. Okay? Alright, and it's approaching 0. and this what makes it gets closer and closer to 0. So remember, the higher your denominator gets, the smaller the number it gets. So if you have like 1/3, that's like 0.333. Add a 4 here, keep the numerator same, that's 0.25. So change in x keeps getting smaller as n is getting smaller. Or n is getting bigger. Alright, so we got a theorem. The existence of definite integrals. Here we go. All continuous functions are integrable. That is, if a function f is continuous on an interval a to b, then its definite integral over a to b exists. So let f be continuous on the closed interval a to b, and let the closed interval a to b be partitioned into n subintervals of equal length, such that change of x is equal to b minus a over n. Then the definite integral of f over a to b is given by the limit as n approaches infinity of the sum that starts from k and ends in n of this equation. So let's make this a little bit prettier, and let's give a thank you out to this guy, Leibniz. He made this much more nicer. So this notation right here is equivalent to that. So let f be a continuous function from a to b. Function d of x is equivalent to change in x. Okay? Alright, so let's look at these. So this is the lower limit of integration. So that's the left hand usually. According since you're going left to right looking at a graph. That's going to be the upper limit. That's integral sign. This is the function given. X is the variable of integration. When you find the value of the integral, you have evaluated the integral. Okay? The integral from a to b of f of x is what that is. So let's do an example. Alright, so we're going to be using the Leibniz notation for this. So the interval -1 to 3 is partitioned into n subintervals of equal length. Change in x equals 4 over n. Let m sub k denote the midpoint of the kth subinterval. Express a limit given as an integral. Okay, so we got from a to b. So this is a, that's b, and that's our function hiding in there somewhere. Okay, so this is going to be the integral from -1 to 3. And where you see fk, you're going to put x, because that's the variable you're using. So you're going to have 3x squared minus 2x plus 5. Now change the change in x to tx. And there you go. Okay, so that doesn't even matter. Definite integral and area. Definite area under curve as a definite integral. So if y equals f of x is not a negative number and integrable over a closed interval a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. So same thing. So this up here is also saying the area, this is the area under the curve, or the sum of all those itty bitty rectangles. Okay, so let's do an example. So we are going to evaluate the integral. Okay, well let's look at our function. So this is a semicircle. We're going to be using shapes. So r equals 2. So if this is a circle, our radius is going to be 2. So this is -2, and now you can't see that. This is 2. So your radius is 2. Okay, so we got A equals pi r squared. Or, yeah, pi. So the area of a circle is pi r squared, but we got a semicircle, so we're going to call that a half of a circle. So that's going to be 1/2 pi times 2 squared, which gives you 2 pi. And there you go. That's the area of the circle, of the semicircle. let's evaluate this. Okay, so I got a shape. Looks like a rectangle. Alright, so the area of a rectangle, I mean a triangle. Why am I saying triangle? Rectangles. Area of a triangle is 1/2 base times height. Okay, let's look at this. So we got the height of 1, and we got a base. We got 1 plus 1, which is 2. Okay, so that's going to be 1/2 times 2 times 1, and you get 1. That's how you find the integral using geometric methods. If an integrable function y equals f of x is below the x-axis, this is what happens. So just look carefully. So it's negative. So it could be made negative, but also what happens, so that's going to make the area negative as well. And this is all it does. It just does this. So this is going to be negative pi over 2, 3 pi over 2 of cosine x dx. That's it. So you're looking at pi over 2, 3 pi over 2, which is right here. So we're looking here. And that is a negative area. So we're just going to put a negative sign in front of the integral. See, that's it. So if an interval does not keep same shape, break into 2 shapes and add the integrals, okay? So for any integrable function, the integral from a to b of f of x dx is going to be the area above the x-axis right here, subtracted by the area below the x-axis, which makes sense. You're adding your areas up, but when you're below, it's a negative area, so you subtract, okay? The integral of a constant. So if f of x equals c, where c is a constant on the interval a to b, then the integral from a to b f of x dx is going to equal a to b of c dx, which is going to be c times b minus a. And I'll explain that, okay? So you got a horizontal line. So you got a thing. It's kind of like our video on the other one. So this is c. So if f of x equals c, so this is c, where c is constant. So it's constant on the interval a to b. Okay? Makes sense. Height times this distance. You get c times b minus a. Right? Okay, so this is a familiar problem. Okay, so a train problem, 75 miles an hour from 7 to 9 is going to be from 7 to 9, 75 dx, which is going to be 75 times 9 minus 7, which is 150. And if you can remember from our last chapter, that is exactly what we got, 150 miles. Okay, and that concludes Introduction to Definite Intervals. Bye-bye.